Okay, so today is a special day because it's Valentine's Day, and we're picking up from the last lecture in relationship theory, wherein we expressed a relationship as a graph, whether directed or undirected. We have our constituents, and then we have these edges, as we call them in graph theory. And this is an example of a 3p poly of constituents. So this is the last lecture. So in lieu of Valentine's Day, today we're gonna take a whole new different perspective as to what exactly relationships are. So in today's lecture, so lecture 2, we will think of relationships as... Yes. Yes, miss. Okay.
Wala kayong date? Ano ba naman yan?
No, miss, I got a date with...
Okay. With math.
With math.
I-study muna.
Sige. Bye-bye.
Bye, miss.
Okay.
Okay. So today we're going to take a whole new perspective on relationships, and we're going to think of them as systems. Systems that can be modeled via differential equations. So I suggest you guys brush up on Reggie calculus, maybe just elementary differential equations. But if you guys don't know or don't want to brush it, I'm going to give it to you guys straight. A differential equation is an equation that contains derivatives. So it could be something like dy over dx plus y equals 0. It could be dy over dx equals cosine of x. It could be dy over dx plus tangent of x equals cosine of x. So these are examples of differential equations. So we're only going with the trivial case of differential equations here, and we will be applying it to love. So this is going to be very important, kind of a good part of this course because we're focusing on the math of relationships and the dynamics of love. So, alright, so let's begin with a sample problem to really nail the point home or nail the concept home. So let's start with a person or two people. I'll call them Bob and Harvey. Bob and Harvey, I won't exactly draw them, but all we know about Bob and Harvey is that they love each other so much. And another thing that we do know that's not psychology based, that's mathematics based, is that we can model or measure their affection for each other via functions of t, where t is some real number. So we can express Bob's love for Harvey as the function x of t, and you can express Harvey's love for Bob as a function y of t. And so what we're basically saying is that at time t, this is the measure of their love for each other. So it's a slide. It's a slider from minus infinity to positive infinity. And then this is a snippet of the real numbers. And the same thing applies for Harvey. So it's a slider where there's 0, 0, and then this is r, or a snippet of r, positive infinity, minus infinity. So this is how we envision them. So at some time t, say time 0, let's say it's over here or over here. So, okay, now that we know how we can model it, let's say that as Bob's, or the rate of change of Bob's affection for Harvey is inversely proportional to Harvey's love for Bob, or Harvey's affection for Bob. So, as the affection of Harvey increases for Bob, Bob starts to lose interest because he thinks that Harvey is a little too interested in him, excessively interested. Okay? And so, his affection goes down. But, okay, let's say this time, but here's the thing. Harvey here likes Bob whenever, at some point here. So the rate of change of Harvey's love for Bob is precisely the same as the rate of change of, is precisely the function of Bob's affection for him. So when Bob's affection for him decreases, his affection also decreases. And likewise, if Bob starts loving him more, Harvey will love him more. But the thing is, because the rate of change of Bob's affection for Harvey is inversely proportional to Harvey's affection for him, it sort of cycles around. In the case we're in, well, Bob starts loving Harvey, and then Harvey starts proportionally loving Bob, but because Bob sees Harvey is loving him excessively, he starts to not love him much, and then Harvey follows suit. And it goes on and on and on. So we can model that via the differential equation dx over dt equals minus y of t, and dy of dt is equal to x of t. And this is an example of a system of equations, or a system of differential equations. So, like in every differential equation or regular equation that we encounter in our mathematical journey, the goal is to find a function that satisfies this equation. Okay? So now you probably can guess that it's probably cosine or sine or maybe e to the x, right? Because you can see them. But we're going to take a different route. We're going to take two different perspectives but come up with the same answer as to what exactly the solutions are for this. And thus the functions that do model the affection between these two men. Okay, so the first step that I want to do is express this in terms of a matrix vector equation. So, okay, it's not really a vector this time, but instead we're going to come up with a vector field. So every point on R2 is assigned with a vector. And then I have a matrix that sort of changes all of that. So we have a vector space, and then we have a matrix that changes that. So I want to express this in terms of that kind of relation. Now, why exactly am I using a matrix and expressing this in terms of a vector? You guys will see soon. Okay, so let's separate out this derivative operator into one singular expression. So this becomes d over dt. And then I'm going to make these two components of a vector, x of t and y of t. And that's equal to, okay. So if I want to express this in terms of a vector, I'm going to want to scale it by some matrix such that we get this kind of output. Okay? Because I can't just have a vector that's minus 1 and then 0 and then have this, okay? What I want is a matrix such that when I multiply a vector by it, or a vector x and y, we would get this sort of configuration. Okay? So we come to notice that if we extract or sort of reverse extract a matrix from this relation, we get 0, minus 1, 1, and 0 times x of t, y of t. Then close. And just to check, it's true. Okay, so I'm gonna apply this, or I'm gonna scale each function in this vector by this dx, dt, dy, dt, and okay, so let's expand this out and make sure we're on the same page here. So 0 times x of t is 0 minus 1 or plus minus 1 times y of t, which is minus y of t. And then likewise, we have to multiply this row by the vector now to get the second component. So that's x of t, x of t, and then since it's a 0, y of t vanishes. So therefore it checks. Same thing. Minus y of t, x of t, same thing. So it checks out. This is exactly what we want. Alright, so what is what is this equation telling us? Okay, so to get a better perspective on the big picture of things, instead of expressing the affections of both of these men as two separate axes, or two separate sliders, let's think of them in a higher dimensional space, namely two-dimensional space. So we have a new picture. This is y of t, and this is x of t. Okay, so just to remind you guys, this is Harvey's affection, and then this is Bob's affection. Okay. Oh, I suck at your cards. Okay. So the vector x of t, y of t, I mean, it's best if we have some slider, right, of time. So this is t. So we have a separate slider, such that when we slide it around, the vector is going to move around or be a different vector. Right? And that's what we ultimately want to do, is that when we slide around t, what exactly is the motion that we're going to get? Okay, so this is it's a vector. It has an x and a y component. So it would be any vector in this axis. That's this over here. So any vector in this entire space, two-dimensional space, is this expression here, or is expressed in this thing here, or this kind of vector here. Okay, so next, why exactly am I using a matrix here? Why is there a matrix here? The reason why I use a matrix is because you guys will see later that what we want is a function that generates a circle in this space. Now, not rectangular per se, but when we plug it in there and then have a computer graph it, it's going to generate a circle. That's what we want, ultimately. This matrix over here is a 90-degree rotation matrix. Because you recall from linear algebra that a matrix ABCD transforms the basis vectors of a system, which is j hat and I hat, the main vectors that make the system look the way it is. What AC does is move I hat to a separate and different coordinate, and BD moves j hat to a different coordinate. And that's the reason why the identity matrix is basically 1, 0, 0, 1. Because these are effectively the coordinates of our basis vectors. They have a unit of 1, and then they are in one direction or the other. They are orthogonal to each other, or perpendicular. Also orthogonal. These vectors are orthogonal to each other. Basis vectors, unit measurement, and then they are orthogonal to each other. So you'll notice here that they don't intersect at all, and that it's just 1, 0, 0, 1. 1, 0 is I hat, which is, x direction, 1, and then 0 upwards. And then j hat is 0, 1, which is 0 in the x direction doesn't move at all this way, but it moves up once. And that's what we originally have. That's the standard for every system. Okay. So what this matrix over here does is rotate the entire thing. Wala po. May nire-record lang po. May nire-record lang po kami.
Pero dapat you have your teacher hanggang ilang minutes pa kayo dyan.
20 minutes lang.
20 minutes. Mag-iisip sa mga kuya dahil natin ha.
Sige po.
Basta may estudyante ka sa loob ng klase daw may teacher.
Okay po. Bilis na po namin. Alright. So, what we want here, what this matrix over here does is rotate this 90 degrees. So j hat becomes, or goes here, and I hat goes over here, or lands over here. Okay, so what we want to find out here is that, okay, I have a vector, and the derivative of a vector, or that vector, is basically another vector tangent to that vector. So here is the derivative with respect to t of this vector function at some time t. So what this basically is I have a vector, but it is 90 degrees rotated. If we have our own little small space at the tip of this vector over here, this 90-degree matrix tells us that that vector that's tangent to this vector is precisely 90 degrees from, or with respect, or it forms a 90-degree angle with respect to our original x of t, y of t vector. And you notice that that does trace out a circle if we let it evolve through time. If we let time go forward, this will eventually sweep out a circle. And what functions do you guys know that generates a circle? Cosine and sine. In fact, the parameterization of a circle is precisely cosine of t, sine of t. And that is why your guess is somewhat right. But the problem is, this isn't the full story. Because when we're given a differential equation, we're usually asked, okay, what exactly is the solution to this given some initial condition? Like at some time t, the function is precisely, or has this precise behavior. What do we want from there? Or how do we solve for those boundary conditions? So that's what we also have to consider. So this over here is not the full story, it's not the full solution. And it is in fact also not the general solution as well. So, alright. Now what we can do with this matrix over here is to generalize it to a different kind of rotation matrix given like this. Cosine of t, and sine of t. Sine of t. Yes?
Who's the research teacher on this term?
Sir Dej.
Sir Dej and some other teacher.
Cosine of t. So we can generalize a rotation matrix at the tip of this vector via this matrix over here.
Rene,
Yeah.
Sir Dej and
Just Sir Dej.
who was walking around, who was
Who's the other teacher?
doctoring during lunch.
I don't know. It was just Sir Dej that I know.
Thanks.
Okay. So this is a generalization of a theta degree rotation of a tangent vector to our original x of t, y of t vector. And what we want to show is that, okay, well, you can see that it is somewhat the same. Except this one over is minus, right? And the sine, cosine. And it makes sense because if we form a triangle at the tip of this vector, this is the angle theta over here, then the sine of here, so this should give us like sort of the components of that triangle, of that angle it's making with respect here. Now notice that in degrees here, so okay, this 90-degree rotation is it's also a half pi radian rotation. So in radians, when we evaluate this matrix, in half pi radians, we will get this matrix over here. So in 90-degree, with respect to this vector, corresponds to this matrix over here. This is just a more general version of this here. So if I have another function, a different function that isn't like this, but we can expand it into a matrix, that's your best bet. This is your best bet. To make it look like this, and then, perform. And what's neater is that this is not only a main problem, but it is a sub-case of a different, more general problem, which is this. d over dt, x of t, y of t, is equal to ABCD times that vector, x of t, y of t. So this problem is a sub-problem of this more general problem concerning two individuals. We can expand it to 3, 4, 5 individuals, but the problem is we lose the geometric intuition behind it. So it just starts becoming algebra. I mean, this is all algebra, but we end up like not being able to use this kind of visual intuition to solve it. Okay, so this is basically what we want, and we just set it equal. We generalize this. All right, so this is like sort of it's not really a boundary condition, but it's somewhat of a boundary condition, but it becomes like this. Okay, but the real, I mean, this is indeed the solution to that, but not quite, not quite. We still have to consider initial conditions. So I have two initial conditions, x naught and y naught. So what do we do with these? We just scale it with these two. So just like how when we have regular differential equation or a very simple differential equation and we integrate it, we have that constant c, because this isn't just a specific solution, but the real general solution. Okay, so this is in fact the solution to x of t. So it's x of t, y of t is equal to this matrix times the initial condition or the boundary condition. So x naught, y naught. So the actual solution is x of t, y of t is equal to x naught cosine of t minus y naught sine of t, and then x naught sine of t plus y naught cosine of t. So I'm just going to remove it. So that is the general solution to our problem. To this, basically. Where A, B, C, D correspond to these three entries. And these three entries correspond to some t degree rotation, either in radians or in degrees. So like how this is an initial stipulation or an initial requirement, this here is our final answer. So just to summarize it, what we do is correspond, given this kind of general problem, we correspond it to some radian of rotation here in our axis, and then it sweeps out a circle. And that's why I said a while ago that it sweeps out a circle. So this is the geometric way of thinking about things. Now let's go with the analytic route. Let's go the analytic road and derive the same result, the same thing here, and this same matrix in the end, using an analytic approach. And it starts with the Taylor series expansion of e to the x. So e to the x is the exponential function, but I'm going to keep that there. So e to the x is the exponential function, but it is not only Euler's number raised to a number, but it is a shorthand notation for a function called x. So it denotes x as some input x, which is a polynomial, an infinite polynomial. Namely, the sum that goes from n equals 0 to infinity of x to the n over n factorial, and that's it. And that roughly goes to 0 factorial over 1, and that's just 1. 1 plus x over 1, which is x, plus x squared over 4, plus x x cubed over 9, or no, 6, and then dot dot dot. Now, what exactly is this? The thing is, if we attach a constant to this, that constant is also incremental or gets the same output, except the n factorial part. So e to the alpha times x is equal to the x of alpha x, which is, so I'm not going to write anymore, it's implied that it's going from 0 to infinity. X to the n over n factorial, alpha to the n. Of course, the sum is implied to go from 0 to infinity, or n equals 0 to infinity. So 0 less than n less than infinity. So that's the input. Now, what we want to do is plug a matrix. So we want to prove that plugging a matrix into this x function gives us something like this. Okay. So, yeah. And the reason why we're doing this is because recall from calculus that the rate of change with respect to x of e to the x is just itself. Likewise, if I attach a constant here, it's just that constant times e to the x. And remember from our original problem, d over dt times some vector v, vector function, is equal to some matrix A times that vector v. And you notice it looks pretty uncanny, or uncannily the same, that we can assume that maybe that vector v could be somewhat, maybe equal to E times that matrix A x. So we want to show that. We want to show that by plugging a matrix into E to the x, we get something that looks like this, and thus a solution to our original problem over here. Okay. So the more general way of solving that, the problem I'll go with A, B, C, D, is to plug that matrix into E to the x. Alright? And then evaluating its Taylor series, and then seeing where it converges or diverges. If it diverges, your problem is probably unsolvable. If it converges, then you got a good model for your relationship. Their given relationship. So, alright, let's do this. So what I'm gonna do is I'm gonna plug the matrix that I showed you a while ago, 0, -1, 1, 0, into this matrix. So we're gonna evaluate x of 0, -1, 1, 0, t. And that expands into n equals 0, infinity. I'm just gonna imply it. Sum is implied. X to the n over n factorial, or no, t, this is t. And then times that matrix, 0, -1, 1, 0, to the n. And if you expand this, you'll notice that it goes into a cycling pattern every 4 matrices. So first matrix, or first entry, second, third, fourth, and then the fifth one becomes the first one again, which is the identity matrix, because 0. And the 0, because we start with 0 over here. The identity matrix 0, 1, 0, 0, -1. Or 1, 0, 0, 1. So there, it starts with that, and then every 4 entries in the Taylor series expansion of this, we get that answer, or we get that. And okay, if we carry on this forever, we end up with the matrix. So if I make this go on and let the computer do it, it gives us with the following matrix. 1 minus t squared over 2 factorial, plus t to the 4th over 4 factorial, plus t to the 6th over 6 factorial, plus dot dot dot. The reason why all of this, all the polynomials are inside the matrix is because when we multiply it to the entries, right, and we add the matrix, and then we expand them into this kind of matrix, okay? And this one is minus t plus t cubed over 3 factorial minus t to the 5 over 5 factorial plus t to the 7 over 7 factorial minus. So it's an alternating pattern over here. And then same thing, but we cancel the negatives. So it's the minus the 3 factorial minus t to the 5 over 5 factorial. Plus the minus t to the 7 over 7 factorial plus. And then the same thing here. 1 minus t squared over 2 factorial plus t to the 4 over 4 factorial plus t to the 6 over 6 factorial plus, or it's alternating. Minus plus, minus plus, minus plus, minus plus. And, alright, this big matrix over here full of polynomials, if you recall your calculus, this looks like the Taylor series expansion of cosine and sine. And there we have it. So, all of this This over here is the Taylor series expansion of sine, but we made it minus. This is sine here, the original Taylor series expansion of sine. And then this is the Taylor series expansion of sine when we multiply it by minus 1. And that's exactly what we get when we do this, do everything here. You get cosine of t minus sine of t, sine of t, cosine of t. Box to end the proof. And there you have it. We get this answer by plugging our original matrix or our original parameter into this exponential function. And then seeing where the sums or where the polynomials will converge. And that shows that this really is our model for Bob and Harvey's affection for each other. How romantic. Very romantic. So I suppose that's it for this video or this lecture. I know relationship theory hasn't been that expounded upon because we're focusing on more different and more complex courses such as algebraic femboid theory and femboid theory itself. But do bear with me when it comes to these things. We have some exciting new topics for you guys here in relationship theory. I just need the teachers to discuss it with me, or I just need more time to make them. So I hope you guys enjoyed this video, and if you guys had a nice Valentine's Day. I know you guys, some of you will be alone, some of you have someone. Me personally, I don't, not at the moment. But I do wish you guys a happy Valentine's Day, and this is a good place to stop.